Hi, everybody. Thanks for coming to the meetup tonight. This is the official meetup associated with the Spark Summit East, which was held its inaugural launch yesterday and the day before. Yesterday and today. Yesterday was the actual Spark Summit. Today was the full day of training. We trained 500 people on Apache Spark today. Tonight we'll have two talks. The first will be by Ram, a Googler who will talk about Spark on Google Compute Platform. The second will be by Michael Armbrust, who's a software engineer at Databricks and the lead on the Spark SQL project, who will be giving a talk about the new DataFrame abstraction inside of Apache Spark that will be released in Spark 1.3. And we're running a little bit late, so I apologize for that. We do have a live stream running. That's what caused some of the delays. Many faces look familiar from the actual Spark Summit, so nice to see you all again. And since we're running a little late, we'll just hand it off to Ram, who will represents Google as the host of this meetup. Thanks a ton to Google, and as always, for both any Spark meetup that has a host. I'm associated normally with the San Francisco meetup, the Spark users, and this is a meetup for the New York, as you all know, meetup group. It's a big deal to have hosts who are willing to feed us, give us booze or water, and also give us the space, which is the most valuable thing. So if you're looking for a job and you're interested in the biggest compute platforms, I'm sure Ram has things to tell you about before he tells you about Spark on Google Compute Platform. Ram.
Welcome, everybody. Thanks for making the time. What I thought I could do in the time we have is I wanted to spend some time talking about the Google Cloud Platform. We introduced that a couple of years ago, and it's really built on our history of building our cloud platform across the world. We have a lot of web serving properties. We built a lot of infrastructure to serve that content over the last 15 years, and really our cloud platform is built on that infrastructure and kind of lives off that network, the storage, and the compute innovations we've been doing in the platform. So when you think about a little bit about data at Google scale, just think about the number of devices that are activated every day. Think about the number of hours of YouTube videos we stream that the platform needs to support. Think about all the pages that you view every day and the search requests that you drive every day. And so when we think about our cloud platform, we want to use the same infrastructure to drive all of this. So when you think about your compute goals, your big data needs, think our cloud platform is really built on the same infrastructure and the same global network across the globe. So when we look at the cloud platform, really we think about multiple aspects. We think about compute, we think about storage, we think about the big data, which is what I'll talk about for most of the session here. We'll also talk about our management and storage needs across the platform. And one of the things to keep in mind is Google has been in the big data space for a while. We've done a lot of innovations in the space. We've released a lot of white papers. We learned a lot of kind of aspects, things around MapReduce, things around column storage and column query, around Dremel, think about aspects around Flume, and quite a few aspects that we've released over time. And parts of our cloud platform is really externalizing some of these innovations that we've done over the years. So if you think about BigQuery, it's really an externalization of Dremel. So really think about column query ability across petabytes of data, running a simple query statement, and we scale seamlessly behind the scenes. If you think about Dataflow, we'll talk a little bit about that's a kind of a data processing pipeline that runs in the cloud, enables you to send any amounts of data. We scale out compute nodes as needed. We execute across both batch and stream. And we also enable a Spark runner that allows you to run that at scale in your own Spark cluster on-premise if needed. So from a platform perspective, there's a wide variety of different pieces. We just released our PubSub connector, Cloud PubSub, 2 days back. That's really our messaging middleware to handle millions to billions of events at scale. And we handle all the provisioning, managing, monitoring, and spinning up nodes as needed. You just send us or give us a topic, send messages. We'll handle everything else. We talked about BigQuery, which is a columnar data storage platform that we have that allows you to query petabytes of data in seconds. We'll also be talking about our processing engine, Dataflow, and of course, from an open source ecosystem perspective, we want you to provide the best cloud platform to run your Hadoop or Spark clusters in the best scale and as easily as possible. So one of the things I want to talk about is how do we enable Apache Spark to run at scale on the Google Cloud. A couple of pieces is we, of course, provide a compute engine, which is really thinking about compute nodes, storage to run the Spark clusters. We also provide deployment tools, and we'll just show a quick demo of that, but how you deploy your Spark 1.2 on a cluster seamlessly, so you don't have to worry about configuring, pushing Spark out each of your nodes. We handle that for you. We also provide connectors, so we provide an HDFS connector, so you can talk to our object store, Google Cloud Storage, so you can have, so Spark can seamlessly read and write from our Google Cloud Storage. We also provide input-output format connectors to BigQuery, so you can have your data sitting in BigQuery, and you can still do all your analysis in Spark and read and write from the data too. And here's a quick, and from interoperability, you can really think about our GCS connector allows you to do Hadoop FS as you'd expect in any HDFS format. We enable you to access that, and we'll just show a quick example of how this works. So to deploy a Spark cluster on Google Cloud, it's bdutil is our open source deployment toolkit. So it's off GitHub. You can download that. And basically, the way you do that, you just call it an extension. In this case, we're doing Spark in Spark 1.2 on Apache 2.4 on Hadoop 2.4. We do a deploy. It spins up by default 2 nodes, 2 worker nodes, and 1 master node. You can, of course, go into an environment that it's a shell script. You can configure it to have more nodes or fewer nodes as you would want. We also provide, as part of this, we've integrated with other vendors. We deploy both Apache 1x and Hadoop 1x and Hadoop 2x. We also have worked with Hortonworks, so you can deploy HTTP 2.2 using the same toolkit, get it up and running. You can have an Ambari cluster up and running. So now once we deploy the cluster, what you can do is actually, if you go to our Cloud Console, this is our what we call the Google Cloud Console, where you can see all your compute, storage, all your big data services. And inside that, you should be able to see our VM instances. So in this case, we'll have our 2 worker nodes and a master node running. Let me scroll down. You should see that up and running. And one of the things that you can also see is if you just want to run a simple classic example, we run a word count on this. So if you come back here and we just go ahead and we SSH into our master node. We provide an SSH tunnel to your master node, so give you extra level of security. And we just go ahead and run that. And so you, of course, have access to all the same Hadoop things. So if I do a SSH proxy, so you think about aspects around, you should be able to see the Spark jobs running. You should be able to see the Hadoop master running. So everything that you would expect from a Spark cluster, you have access to that, and be able to deploy that with one command line, get it up and running, get your jobs running, and of course you can start accessing all your data sitting on GCS. So one of the things you should notice is that the actual command line is actually referring to files sitting on our GS. So GS points to a Google Cloud Storage. So basically, it's a URI pointing to Google Cloud Storage. If you go to our storage browser, we go to our input to where the files are, and the first thing you'll notice is all the files are there, and also just the job that we just ran, the output also gets written out to our to Google Cloud Storage. So really, you have a kind of think of it as having a permanent storage in our Google Cloud Storage. You can spin up clusters up and down. The files stay over time. You can also think about things around parallel cluster execution, where you have multiple Spark clusters all running on top of the same storage. You can have maybe a Spark SQL cluster running. You could have something doing batch processing, or you can have a streaming job running. The next thing I want to do is I want to invite Ray here just to do a quick demo also of we also introduced a data processing toolkit called Dataflow. And I just want him to run a quick demo of that so you can see how that works. Go ahead. Ray, if you want to just run quick.
Hello? Yeah. All right, cool. So my name is Ray. I'm a developer advocate here in the New York City for the Google Cloud Platform. And the Cloud Dataflow, it's a programming model where you can do batch processing and streaming processing. And the way that you write it, let me show you very quickly, is in a way, sorry, I'll show you in the code in a second. But the way that you write it is the way you would otherwise want to, is very idiomatic. So you can do it the way that you want to process the data. I'll show you the code in a second. But it is an open source SDK where you can use to write data processing pipelines. And then you can deploy it onto the Google Cloud Platform to actually execute it as a running. And in the Google Cloud Platform, we can then scale up the number of instances to manage and execute and process as much data as you need to. And this whole thing is also open source. And instead of running on the Google Cloud Platform, you can also run this in Spark as well. So let me show you the code very quickly. So here we have a code. Let me explode this up a little bit. It's also a word count application, but as you can see, it's slightly different from the other word counts. Here we have some things called data flow pipelines, where I can apply different transformations to read the file, count the words, and then write the count out. Right? It's pretty simple. So I'm going to run this on the Google Cloud Platform. So here I have an example. So this is running a Java application, and it's going to read the file and then write it to the output. And this pipeline has, I think, 3 stages. There's the read, the count, and the write. So if I actually go to the console, make sure this is off. I'll wait for it to spin up. But if you can actually see it, when it's actually running, you can see its status. So here we can actually see the 3 pipelines at one after the other. So reading the line, counting the words, and writing the counts. And for every single one of these steps, you can also go in and see the logs. You can see the statistics of the number of records that's being processed. Right. Yeah. Yeah. Exactly.
Actually, no. You run it from any. We can run it from your. The Maven job's actually running on the local computer on the laptop.
On the laptop. Yeah.
It just points. It just goes directly to the Google Cloud to execute.
So you use the Google Cloud Java API to send that to the Google Cloud.
That's right. Yeah. And the reason it's taking so long is we have to stage all the jars to the Google, all the dependent jars to Google Cloud for the staging thing, and then the job actually starts executing. And of course, we have options where you can read pre-stage, so once it starts executing, you don't have to do that step of staging every single time.
Yeah. So here in the console, actually, this is running right now, so you can see this is actually running. So when it finishes, you'll see the final state. So I'm going to show you actually how to run this in Spark as well. So with Dataflow, you're writing the description of how you want to process the data. Now, how the processing is actually executed depends on the platform. So here's the way to run it on Google Cloud Platform directly. But on Spark, I can also do very similar things. So I'm going to go back to IntelliJ. And here we have a Spark word count. Load this up. And you can see the way that you process data is very similar. It's almost exactly the same way. With the only difference here is that I'm specifying that the execution is going to be taking place in Spark. And here I'm specifying the master node as well. And I can actually go back to the command line. And not sure you can see this, but this is actually doing a Spark submit. Sorry.
One more.
Yep. That one. Yeah. It's doing a Spark submit and doing the Spark word count. And I can run it just like that.
In this case, it's actually running on the master node in Google Cloud.
Yeah.
Just a question. Is this managed VM or
Sorry, the question was, is that a managed VM? It's just straight GCE VMs. So we just spin up straight GCE VMs. So you can see the VMs on running in the GCE VM instance.
so you have a direct access,
You can SSH it to the VMs. It's a straight GCE VM. You can SSH in, and once you go in, you can bring up your Spark master web UIs are running, the other UIs run, just as like any other Spark cluster.
Now, the benefit of doing this, though, is that when you're describing how you want to process the data pipeline, Dataflow can actually optimize the MapReduce job that gets generated behind the scenes. So once you have the processing graph, we actually do a lot of optimizations to reduce the number of MapReduce jobs that's necessary to process the data. And the way it actually optimizes is really, really efficient. In some cases, it's even better than the manual optimizations as well. So the Dataflow, you have the SDK. You saw the monitoring tools. And it's managed service on the Google Cloud Platform, where we can actually scale up the number of instances that's necessary to process the data. and you saw the console where you can see the status and everything else. Yeah.
Excuse me, can you give an example of, you were saying in some cases it's even better than manual optimization. Can you give a concrete example?
So there's actually a lot of other slides that's not here, but we can catch up offline. Yeah.
In general, I think we analyze your DAG graph, and based on that, we think of about how many additional compute VMs we want to spin parallel for each parallel execution part, and so we think of the optimization behind the scenes. So if you can either, if you know your job better than Dataflow, then you can specify the number of workers you want to run. But if we can analyze, we also do some level. If you don't specify that, we analyze that and we spin up the number of parallel workers for you. Does that make sense? So that's what we mean by managed services. Tuning, optimization, monitoring is all managed by the cloud platform. And go ahead.
I've got two questions. One is, I think it's for Databricks, right? So I went to the summit. I see Databricks using the AWS. So does Databricks using also Google Cloud?
It may not be on there.
So the question was, does Databricks Cloud work on Google Compute Platform? The answer is not yet, but it is on the roadmap.
Okay, and another question is, we're using AWS, right? So what do you think, it's for Google, compute, right? What do you think they will convince other people by migrate from AWS to Google Compute?
Yeah,
Will you repeat it quick?
Yeah, why will people move from, say, AWS to Google Cloud? I think a couple of things. I think the way I think about it is, we've been in the cloud business for a long time. I think we have one of the largest, we do think we have the largest cloud infrastructure in the planet. The other aspects, I think, where we feel, that's from a scale perspective, but I think the other aspect where we feel we differentiate is really about ease of use and developer productivity. Our goal is to reduce the need for DevOps in the cloud, right? So a lot of the services that we provide in the cloud platform is all about how do we make life easier from a developer perspective, reducing the need for DevOps. Our legacy was really the strength of Google App Engine, where we basically manage your entire website, and without the need for DevOps. Snapchat is a great example. They're serving up billions of messages every day based on just App Engine with very few dev operations. Another example is what we're doing today with BigQuery, right? You think about someone running a query across a couple of petabytes of data, and they don't need a DBA. We handle it for you behind the scenes. So that's really the strength where we feel we differentiate the competition, as we say, let Google figure out how to deal with containers, with your VMs, with scale, with management. Because we've been doing this for so many years, we can automate a lot of these aspects and let the developers really focus on cutting code, which is what most folks want to do, and not deal with shell scripts of deployment and those aspects. That answer your question? Other questions? I think the one last thing is, one quick question. How many of you have heard about Google Cloud before this meetup? Oh, this is good, more than I expected. Our marketing guys are doing some good work. The thing to also get is we do offer a credit. So if you guys want to try, if you're new users to think you want to try out Google Cloud, you heard about it, go to cloud.google.com. You get a $300 credit for 60 days, and you can get running. Cloud Dataflow, Google Dataflow. It's an alpha right now. We're going through a whitelist. So if you guys are interested, we're looking to do a beta very soon, but it's an alpha right now. So if you guys, right now it's by whitelist alone. So if you guys submit online, if you go to cloud.google.com/dataflow, you can submit online, and our PMs are always eager to get more people into the funnel. So. Okay, then you should talk to me after this, and let's figure out how to get you on that thing. Okay? I know before Andy gives me the hook, I also wanted to introduce Susie, who's a usability researcher who's always looking for folks to talk to, and she has swag and business cards to hand out.
Hi, everybody. Welcome to Google. I'm Susie Sorochak, and I am the senior researcher for all of our big data and storage products in the cloud. And we're always looking for participants to take part in usability studies. These studies are really important for us to not only better our designs, but also help us plan our future product roadmaps. We do all sorts of studies, everything from surveys to in-person lab studies and interviews, and sometimes we even come to you and do field visits. So I am here to try and encourage people to sign up. We're looking for customers and also potential customers. So even if you're using our competitor products or open source products, you would still qualify. So and also for participating, we typically give incentives for people, especially if you take part in like an hour-long session. And I have some incentives for you today for signing up. So I've got some cards with the link for the sign-up sheet, and then I also have some Google Cloud Platform stickers. So thanks to the speakers for giving me 2 minutes to convince you guys.
So thanks to Ram and Ray. Let's clap for them. So as somebody that has a passion for seeing Apache Spark get driven into every corner of the world, having Spark run on any platform, especially one as kind of pervasive as Google's, is really cool. Next up, we have Michael Armbrust. He is a software engineer at Databricks, and he's the lead on the Spark SQL project, and he will be talking to you about the probably most exciting thing that's happened in Spark since 1.0. That's the DataFrames abstraction.
Thank you very much. So I'm here to talk about this kind of really cool new API that we just released last week as part of Spark 1.3. I'm going to show you how you can kind of go beyond SQL and speed up kind of every Spark job that you write, even if it has nothing to do with SQL, using DataFrames. Before I dive into that, though, I want to give a little bit of background about myself and Spark SQL. So Spark SQL is part of the core Spark distribution. If you download Spark from the Apache website, you get it. Many of the vendors actually also ship it, although most of them don't support it yet. But it's actually one of the most active areas of growth within the Spark community. As you can see on these charts, the number of unique contributors continues to go up. It's pretty awesome how many people have added code, even though the project is less than a year old. And the activity is really ramping up as well. You can see last month in particular, as we were really kind of adding this new DataFrames API, things have gone pretty crazy. It's to the point where now really some of the most exciting advancements that are happening in Spark, we're asking, how can Spark Core make Spark SQL faster? Since it turns out this is actually a very common pattern for many Spark jobs. One thing I'm also pretty happy to announce, up until this most recent release, Spark SQL had an alpha tag, meaning that we were not guaranteeing API stability. We take API stability very seriously in the Spark project. If you write your programs against any of our public stable APIs, we guarantee binary compatibility across the entire 1.0 series. And so starting with the 1.3 release, anything that is public and not marked experimental inside of Spark SQL will have those same API guarantees. So what do you actually use Spark SQL for? So a very common use case is to use it to actually run SQL or Hive QL queries. And as part of this, we have a lot of integration with Hive. So you can actually just take your hive.site XML file and put it into the configuration folder of Spark, and we will connect to the metastore. We will read your existing Hive tables. We will use all of the Hive UDFs that come kind of from their catalog, and also your own custom UDFs will also work with Spark SQL. We have wrappers to do this adaptation. And so a very common use case is people are just replacing Hive in order to get kind of faster performance with Spark SQL. Although one thing I will say is that this is optional. You should use the Hive context. You should use Hive QL even if you've never used Hive before. If you don't have a previous Hive installation, we automatically create a metastore in the local directory for you. So you can kind of have all of this power without having to do any of the configuration. So as many of you may know, SQL is kind of the lingua franca for doing data analysis and business intelligence. And so another very common use case for Spark SQL is actually using this as the kind of gateway to data in HDFS. So you've got JSON data or Parquet data or log data. You can connect these existing tools to these new data sources through Spark SQL. So we work alongside with Tableau and Zoom Data and Click, and you can kind of use this interconnectivity to get access to new data. But of course, it's not just about SQL. I think one of the really cool things here is you can kind of mix and match your SQL alongside Spark programs. So we have rich language bindings in Python, Scala, and Java, just like the rest of the Spark stack. And so you can express a SQL query at the beginning of your job to extract data from a database, maybe join it with some demographic data, and then the things that don't fit nicely into SQL, you can immediately drop into map and reduce and filter and all of the kind of Spark operations on RDDs. And really going back and forth between these two worlds is relatively seamless due to this rich integration. So like I said, my name is Michael. I put my Twitter handle up here because these slides are actually posted there. So if you want to kind of follow along or see these afterwards, check that out. And like Andy said, I am the kind of initial contributor and lead developer of Spark SQL at Databricks. So OK, that was a lot of SQL. But I'm here to tell you a secret. Don't tell Mate, but Spark SQL is actually not about SQL. If you are staying away from the Spark SQL project because you think SQL is for old people wearing IBM suits, never fear, come back. And now, don't get me wrong, SQL performance is very important to us. I don't want to be misinterpreted here. We do run all the SQL queries. This is a benchmark TP-CDS, which is kind of the standard for distributed databases today. This is a comparison of the performance to previous systems that did SQL on top of Spark. And as you can see, we are faster across the board, sometimes by as much as 8x. But enough of that. What I really want to talk about today is how Spark SQL is really about quite a bit more than SQL. It's really about the best parts of SQL, which are the query optimizer and declarative data flow. It's about making, so really what it comes down to is it's about enabling you to create and run Spark programs faster by writing less code through high-level operations that the DataFrames provide, by reading less data. So kind of, when you're doing a large job, if you're only interested in data from this year, we can help you skip over all of the data that's not important to you. And really what this comes down to, kind of like I was hinting at on the last slide, is letting the query optimizer do the hard work for you. You tell it what your data flow should look like, and it figures out the best way to execute it. So at the core of this, it may be no surprise, is this new abstraction called DataFrames. So what exactly is a data frame? So a data frame is a distributed collection of rows. So that kind of sounds quite a bit like an RDD, right? RDDs are distributed collections of data. But instead, we have these rows where we actually name the columns. So it's like an RDD, but where you have a lot more schema information, where you're telling Spark about the structure of your data so it can exploit that structure to make the program faster. Now, of course, we didn't actually come up with this idea on our own. We were heavily inspired by a bunch of really cool DataFrame libraries that are out there already. We drew a lot of inspiration from our DataFrames and Pandas DataFrames. And the really nice things about these libraries is they give you this very simple abstraction for doing filtering, selecting of columns, aggregations, plotting, kind of really it's like a statistician's toolkit. And what we wanted to do is bring that kind of expressiveness to Spark. And that's kind of what we're trying to do with the DataFrame API. Now, some of you who have been following along the Spark SQL story for a while may say, wait a second, this is sounding a lot like a schema RDD. And that's true because it is a schema RDD. It's just not called that anymore. We wanted to change the name both kind of as part of the stabilization of the API, but really what it comes down to is this is kind of a name that developers are more familiar with. And also because of some unification that we did inside of the API, a data frame is not actually an RDD through inheritance anymore. You can very easily get an RDD from it by calling .rdd, but what we did with this release was we actually unified the Java and Scala APIs, and the Python API. So really they're kind of uniform across the languages, and as a result we had to kind of, because their Java RDDs and Scala RDDs are different, we removed this inheritance from the hierarchy. So as of Spark 1.3, use DataFrame instead. So do a find and replace in your code. OK, so what do you actually use DataFrames for? So the first thing I want to talk about is the way you can write less code by using DataFrames abstractions for reading and writing data. One of the other kind of really cool features that is part of the Spark 1.3 release is the data source API. And what this does is it kind of provides these wrappers that allow you to encapsulate the rules for connecting with other data sources and translating them into Spark DataFrames. So kind of out of the box, if you just take Spark SQL, you can already read JSON data. You can use JDBC to connect to existing other SQL systems. You can use Parquet, Hive, MySQL, data on S3, and so basically I think what's really cool here is you can read all these sources without having to write a lot of the boilerplate. It's also an extensible API, so kind of people outside of the Spark, the kind of core Spark distribution can add on their own custom data sources. So at Databricks, we released a data source for reading Avro data. We also released another data source for doing CSV data. People in the community have added libraries for reading DBase, and there's work in progress on HBase, Elasticsearch, Cassandra, Redshift, and more. So it's not just, once you've got the data in, now you have to do processing with it. So another kind of really important part about the DataFrame API is these common operations that can be expressed very concisely as calls to the DataFrame API. So saying which columns you care about and doing kind of simple transformations on those columns. Joining data from different sources. Once it's a data frame, it doesn't matter where the data came from. It could be joining MySQL data with data off HDFS or JSON data with Parquet data. This is kind of a skinny waist for the Spark stack when you're trying to bring data together. It also supports aggregation, such as count, sum, average, and of course filtering. So if you're an existing Spark user, you're probably already familiar with the kind of how Spark's expressive APIs allow you to write less code. I want to walk really quickly through an example here. Consider you have a text file, and it has a whole bunch of names and ages separated by tabs. And I want to figure out the average age for a given name. So I want to figure out that all the kids are named Aiden, and Gertrude is a much older name, or for example. And so this code actually kind of does that with Hadoop. And I won't walk through it line by line, but at a high level, you're writing a map function that is bringing the data in, parsing it, and outputting it. And then you're writing a reduce function that adds together the sum and the count, and then divides them at the end to get the actual average. That's a lot of code just to do an average. Obviously, in Spark, it's quite a bit shorter. But still, the structure is pretty much exactly the same. You're reading the data in, doing some manual parsing. And there's a lot that's left to be desired with this code fragment, right? Like, I think an average developer coming in and staring at this would have to look for a while before figuring out what it was doing. It's also not obvious what 1 and 0 are as I index into my tuples. So it's not very developer friendly, and it's still quite a bit of boilerplate for what should be a simple operation. So with DataFrames, this is actually quite a bit simpler. You'll see up at the top, we start by reading in from an already structured data source. So we don't have to worry about parsing. Kind of the system is taking care of that for us. We will do a group by, we do an aggregation. It's all by column names. And then, of course, because it's Spark, we call collect to actually get the answer. But as you can see, this is quite a bit more expressive and quite a bit more developer friendly. This is just a kind of very brief sample, but we have full API docs up for all of the languages that we support. So check out these slides and follow those links if you want to learn more of the functions that are supported here. But it's not just about writing less code. Of course, when you're doing big data analysis, it's very important to have efficient implementations. A question I get asked a lot is, what is the penalty that I'm paying for writing my Spark programs in Python instead of in Scala or Java? And because Python is an interpreted language, so sometimes there is some overhead to writing in that. But the nice thing is when you're writing data frame operations, you're only constructing the flow of the data in Python, and all of the actual work is being done in a highly optimized implementation that's actually running on the JVM. So what you'll see here is if you compare the average from the previous slide implemented in Python just using RDDs and with a RDD implementation in Scala, kind of a relatively naive implementation there, to the heavily optimized data frame implementation in any of the 3 languages, you get quite a bit better performance using this high-level declarative API. So you can kind of get the power no matter which language is your preference. So I want to take a break from the slides real quick and do a really quick demo to show you what it's like to actually use DataFrames. I'm going to switch over here to Databricks Cloud. For those of you who aren't familiar, that should be readable. Basically, what this is it's a hosted environment for running Spark clusters. And what we do is we provide you with notebooks. So a notebook is kind of an interactive environment for running Spark commands, plotting them, and sharing the results with your coworkers. Now, of course, open source is incredibly important to us at Databricks. So everything that I am typing into this notebook can also be done in the Spark shell. I just much prefer typing in a web browser because it's pretty cool. So let's start off by loading in some data. I've taken a whole bunch of JSON data that holds all of the different Spark commits that have ever been made to the project, and I put them on S3. And I'm going to read them. Just kind of let's do a head here to see what the data looks like. And when I want to actually load this data in, all I have to do is call this new unified load API. So no matter which data source you're reading from, you can do SQL context load, point it at the data, and tell it which driver, which data source API to use to pull it in. Once the data is loaded in, you can see it automatically infers the schema from the JSON data. So it's up to the data source to provide the schema to the system so that it can understand the structure of that data. And one of the nice things is we also support complex nested types and arrays. So if we look at this in tree form, you can see that this actually contains like an array of files and other things. And all of that structure is preserved even after loading it in. So once I've got a data frame, I can run commands on it. So let's take a look at like, the first row, for example. So kind of relatively familiar Spark commands here. But when I want to pull out individual fields, it's pretty easy. So I can do select. We can pull out, just the author name. We can also do filtering. So if I want to filter on the author name being me, pull one out there. You can also do aggregations. So if I want to pull out, do the count of all of the commits that I've authored. And you can make it relatively easy to do comparisons as well. So if I want to see, how many have I written versus how many have I committed, you can see that these days I actually spend quite a bit more time reviewing open source contributions as compared to writing code, which is a pretty cool place to be in. So that's a relatively simple example, but you're saying, okay, that's simple SQL stuff. I've got complex machine learning functions. I've got very nasty regexes and things. I want to be able to use Python inside of these data frames. So in this example, I want to extract out the domain name from the email addresses. So I've written some Python code to do this. It's just kind of a relatively simple regular expression. But now I want to use this inside of data frames. So if I just do get domain equals, and I just call the UDF function, and I'm going to pass the UDF function a Lambda function. And I'll take this code, replace it with the input from the Lambda function, make it robust to bad data, which is important. And so now I've actually created a UDF that can be used inside of a Spark SQL data frame. So if I do df select get domain, df dash, you can see it pulled out, Gmail is very popular amongst the Spark committers. And so once I've used this UDF, now I can immediately drop into more complex data frame operations. So if I wanted to do an analysis of, what are all of the domains of, all of the commits that are coming into the system, we can do a group by, and I'll assign an alias here. So I can group by the domain, and we'll count, and I only care about the top committers, so we'll do an order by count. So I've grouped, I've aggregated, I've done a count, I've taken the top 10, and you can see now we have a list of the most popular domains amongst Spark committers. And you can kind of see the Berkeley roots of the project live on. And so, okay, so that's great. But we also want to be able to interact with other libraries that we're already familiar with. I want to do plotting. I want to do other kinds of aggregation. And so one of the really cool things is you can take these data frames and immediately turn them into pandas data frames. So if I just bring up matplotlib, run that same command, and all I have to do is call two pandas on any data frame, and it immediately becomes a pandas data frame. So that collects the results down to a single machine so it can be used inside of pandas. And now I can pass it to the plotting thing and get out kind of fancy pandas plots with all of the power of matplotlib. Yes. Yep. That's a good question. So the question was, this Lambda function is written in Python, so you're actually going to have to fork a Python process and stream the data out in order to compute that UDF. Is there a performance penalty to doing that? And the answer is yes. Scala UDFs don't require us to ship the data to a different process, so they will be faster. But this is a question of efficiency versus developer time. So I think it's really kind of up to your particular use case which language you should write in. Okay, So I want to talk a little bit more about some optimizations that Spark SQL makes. And another really good way to speed up your data processing pipelines is to actually just not read as much data. And Spark SQL makes it easy for you to do this automatically through several methods. So kind of the first one is relatively simple. It's just converting to more efficient formats. If I've got a bunch of JSON data and I'm going to be reading it over and over again, that's a really bloated format. It's got a lot of extra, every single column name is there for every single record. So using this unified load and store API that I showed off, I can load in as JSON and save out as Avro data and kind of immediately get significant performance benefit. And this is, once again, using DataFrames as the narrow waist of data transfer within the Spark ecosystem. Another thing you can do is, a lot of times you have very wide rows with a whole bunch of columns where any given analysis actually only requires a small subset of those columns. So why am I reading all of the data every single time? There are formats like Parquet, which are also kind of supported by Spark SQL, where instead of storing all of this one row at a time, they store all of the columns for a file in a single block. And then there's an index at the end of the file that allows you to jump immediately to the one. This is actually inspired by Google's Dremel. And so you can kind of get this power also just by by storing your data as Parquet. When you do things like select or filter, we automatically reconfigure the Parquet input format to take advantage of these operations. So you could do it by hand, but it's actually quite a bit more code. Another thing is partitioning. So a very common pattern, if I've got data that is organized by time, is I'll actually put it into folders, where all of the data for the year 2014 goes into a single folder. We support this kind of through the standard Hive way of doing it. And starting with Spark 1.3, if you just point our Parquet data source at any folder, any set of folders that has this structure, we will automatically scan it in parallel, figure out all of the partitions, and kind of automatically prune out folders when queries have predicates that allow us to. Another trick that we'll do, even if you don't do any organization of your data, is we can actually skip data using statistics. So for example, in Parquet, for each column, we will keep around the minimum and maximum value. So if I know the maximum value for a given file's year column is 2012, and I'm doing a query for 2015, obviously we could just skip that file entirely. So this is something that kind of happens automatically. You don't even have to do any extra organization of your data. One thing I will say is this is currently turned off by default due to bugs in the Parquet library, but they are publishing a new release hopefully very, very soon. And as soon as we get that, we'll flip it on by default. But if you read through the tuning guide, there's the options to turn it on automatically. And then finally, we can actually also push predicates into other storage systems. So if you connect this to another SQL database and you write Spark SQL queries against that table, we will automatically construct other SQL queries to send to that system so less data is transferred over the network. So really, at the core of this, I've been talking a lot about the optimizer, but there's this thing called Catalyst, which, once again, since we're at Google, was actually started, the initial ideas for this came from a research project that I did as a postdoc at Google. But the kind of cool thing here is whether you're writing in SQL or whether you're writing using the DataFrame API, all you're doing is constructing a logical data flow plan. And the rest of the optimization after that is exactly the same. And the cool thing about optimization is we don't just pick one way to run your query. We actually enumerate several possible physical plans and then pick the cheapest one for you automatically. And an important thing to understand about optimization is, like the rest of Spark, we do it as late as possible. We wait until you've constructed your entire data flow and given us an action before we actually try to figure out the most efficient way to do it. So this means that Spark SQL can even optimize across functions. So to make it kind of more clear what I'm talking about, I want to walk really quickly through an example. In this case, consider you've got some stream of events, and I want to do some machine learning on these events. So step one is to join it with demographic data for the users that those events they're actually performing those events, so that I have extra features to use in my machine learning algorithm. So one of my coworkers has written this function add demographics. And as you can see, it's a relatively simple function. It loads some table from Hive. It joins on user ID, and then it does a little bit of extra augmentation to make sure I've got all the features I need. So I actually want to know what city the user is from, so I'll run this UDF zip to city that does a lookup. And then it returns a new data frame that has been augmented with all of this extra information. So then I come along, I've got a bunch of data stored in JSON, I pass it in to this function, And then I want to do some filtering. So I'm doing a very New York-centric analysis. So I filter out anything that's not from New York. And the only column I care about is timestamp. I'm really looking for some temporal patterns. And so the trick here is that this filter, unfortunately, is up at the top of this data flow in the way that I've constructed it. My coworker didn't give me any way to push that filter down to say I don't care about that. And the reason this is bad is because that join is now very expensive. I'm joining all of the users across the entire world when I only care about New York. And so what Spark SQL will do that can't be done when you don't understand the logical structure of the query is we'll actually push that filter beneath the join so that we can only do the join on relevant users having already filtered. So that's pretty cool. But another thing that's really nice here is if your data sources change or other things change, we actually will redo this analysis to find even more efficient ways to do it. So I was writing this analysis using JSON. It's very nice, human readable, easy to debug, and I just have a simple Hive table. But if I want to move this into production, I want to speed things up. So I changed the data format to Parquet, and I partition the Hive table so that I can kind of get access to it more quickly. Spark SQL will re-optimize this query and pick a plan that will do predicate pushdown and partition pruning automatically. So since we think DataFrames are pretty cool, we're actually kind of using them more and more as a common abstraction throughout the Spark platform. So another really awesome feature that came along with Spark 1.3 is this idea of machine learning pipelines. So DataFrames are the thing that get passed through, since a lot of what you want to do is pull out individual columns, do work with them, pass it on, augment, add more columns. And so this is an example of a machine learning pipeline where you're kind of passing the information through. Basically the input is a data frame and the output is a model that has been fitted to a data frame. So that's kind of the conclusion of my talk. It's really about how Spark SQL DataFrames can let you write your Spark programs faster by writing less code, reading less data, and really letting the optimizer do a lot of the hard work for you. I'm happy to take any questions. Yes, and there's a microphone.
Yeah,
if you
can
want
you go to one of these
talk into the
microphones?
microphone.
Oh, yeah. So a question, you mentioned like machine learning with Spark SQL.
Yep.
And then in the summit, I also see the machine learning with Spark streaming, right? Do you see any use case with Spark SQL and then Spark streaming?
I would love. So yeah, that's a great question. I would love to have more integration with streaming. So today, kind of the typical thing that you'll do is you'll use streaming to do some initial processing, and you can either register the resulting RDD as a temporary table, and can convert it into a data frame and register it as a temporary table, and then run interactive queries on the data that is coming in. Another thing you can do is you can actually use streaming to write the data out in one of our formats such as Parquet, but we do not yet have the ability to write SQL queries that construct streaming jobs. That's something we've thought about. There have actually even been prototypes by Intel China, but there's kind of nothing production ready yet at this point. Any other questions? Yes, over here. Yeah, so the question was, will there be a mechanism to take advantage of more cores? Say, for example, you're running on Google Compute Engine or Amazon and AWS. Can I just kind of automatically scale up the cluster? And the answer is yes. Spark's actually very tolerant of this. And we've been doing more work to make it better for scaling up and down, particularly when you're in a Yarn environment. So in Databricks Cloud, there's actually a button next to the clusters. You click configure, and you can make it bigger, which is pretty cool. And it just automatically grabs more machines. But I guess when the other new feature that actually makes this much better, particularly when you're on Yarn, is what we have is when you're doing a shuffle, kind of a very common problem is you grab a whole bunch of machines, you do a whole bunch of shuffle, and there's a couple of stragglers. Because of the way Spark Shuffle works, you actually have to kind of fetch those files from the map task that was doing them. So the map tasks have to sit around taking up resources for a very long time, even though they're not doing anything other than waiting to serve up some files. So I believe it was in Spark 1.3, we added a special external shuffle service so that even after Yarn has reclaimed those resources, you can continue to serve those files and not have to recompute them. So we definitely do take scaling up and down very seriously. We'll take another question, then come back.
Is
there a good way to cancel the Spark SQL query?
Yes. So the question about cancellation, that you can cancel queries. Basically, the way like I could do a demo in Databricks Cloud again. There's a cancel button, but the trick that we're doing under the covers, which is totally open source Spark, is you create a job group before executing the query, and you can cancel. Yes. And then you can kill the job group. So and that, all of SQL execution is RDD work. We're building on top of core. So when you want to cancel SQL queries, you cancel them the same way you cancel Spark jobs. Yes.
How is Hive on Spark different from the Hive context itself?
Yeah, that's a very good question. So these are kind of different projects with very similar goals. It's to use Spark as an execution engine for running Hive compatible queries. The key difference is Hive on Spark is still Hive. It is the Hive optimizer with a different backend. And so I think kind of it's maybe more of a drop-in replacement, but at the expense of tight integration with kind of the Spark ecosystem. So you can only do SQL, and you can't kind of operate with RDDs in the same way that you can with Spark SQL. Let's go around. I'll come back.
Can you step to a microphone just because we're going to have this on YouTube?
You had just mentioned Spark interaction with Yarn, but it also works with Mesos.
It does.
The same functionality with Mesos as with Yarn. Or would you prefer that we use Yarn instead of Mesos? Or I'm a little confused.
Oh, we definitely don't have a preference. We would like Spark to run on as many platforms as possible, and we work with both the Yarn community and the Mesos community to make sure that Spark runs well there. Spark was originally actually inspired by the Mesos project. It was like it started as an example of how easy it was to build frameworks on top of Mesos, and then like spun off into its whole own thing. But you should basically, I think external requirements should drive which one you're using. I don't think there is a preferred one. Today, I think there is slightly better support for scaling up and down with Yarn, but we're working with the Mesos people to get that same support there.
So within a few months, the Mesos should catch up with you.
I would hope so, but like I said, I'm not an expert there, unfortunately.
I know you're not a lawyer, and you're not.
Yeah, not a lawyer, not a business person. Don't take me too seriously.
But you can see the reticence to using Mesos if Yarn's got more support for certain of these functions.
Really, that is a relatively niche feature that is mostly good if you have a lot of the batch jobs running on the same cluster sharing resources. That's where that feature really matters. So if that is part of your workload, yes, you should probably run on Yarn today.
But that's probably the only case, or I'm not.
I don't know.
But you see what I'm saying?
Sorry.
It just opens things up to questions.
Yeah, I mean, I think really both of them are pretty well supported.
Okay, thank you very much.
Yes.
So you mentioned about the Hive Metastore, that it will automatically connect, but if you don't have one, then it automatically creates it.
That is correct.
Can you expand on that a little bit? You said it's actually created in the local directories. How is it shared across different workers and things like that?
Yeah, it's a good question. So this is all kind of like Hive standard stuff that we take advantage of inside of Spark SQL. Hive has the ability to run against several different databases. You can run it against, you can have the MySQL, the metadata stored in MySQL. You can have it stored in Postgres. You can have it stored in Derby, which is an embedded Java database that runs inside of the JVM. And so what we do inside of Spark SQL is by default, if you don't provide any other configuration, we use Derby in the local directory. You cannot share it with other processes, but you can have persistent tables that will come back when you stop and restart your program. If you want to share it with other people, if you want to have multiple Spark contexts talking to the same metastore, then you need to configure it to run against MySQL. And kind of all of the directions for doing that are exactly the same as the directions for doing it with Hive. Okay, I'll stick around for more questions, but thank you very much for having me.
Let's thank Michael. Just a few more people to thank, because these sort of events take a lot of energy. Matt Hunter at Bloomberg is a active member of the Spark NYC meetup group and was pivotal in making sure this event happened. He was the connection to the friendly folks here at Google, and I wanted to make sure that all of the work that he put into planning this with me got acknowledged. In addition to that, let's clap for Matt. In addition to that, the actual organizers of Spark NYC, Jason Shao, Francois Lalai, and Daniel Fry, are deserve a round of applause. They're not. I don't know if any of them are here tonight, but they are friendly enough to were friendly enough to host us in the broader sense as visitors to New York. And so I'm sure that they are also interested in any of you who are willing to host further meetups and working actively on Spark to keep the Spark NYC meetup group going strong. Two more things. The Spark Summit in San Francisco is open for registration, and we hope to see you there this summer. And let's most importantly thank Google one more time, Ram, Ray, and Michael as our speakers tonight, and Google as our host. And that's it.